Okay. Good afternoon, everyone. It is my pleasure to introduce our colloquium speaker today, Dr. Yang Li. So he received a bachelor degree in telecommunication engineering in 2006 and a master degree in electromagnetic field and microwave technology in 2008 from Hongzhou University of Science and Technology in China, and a PhD degree in electrical engineering in 2012 from Iowa State University. So he's currently a postdoctoral fellow in Eric Mazur Group at Harvard University. His research interests include metamaterials, photonic crystal, linear and nonlinear nanophotonics, microwave non-destructive evaluation, analytical and numerical methods for electromagnetics, antennas and antenna arrays, microwave remote sensing, so a lot of different research area. So he received the IEEE Antennas and Propagation Society Doctoral Research Award in 2011, and he was also nominated for the King Award in 2013. So Dr. Li is going to talk to us about zero index on a photonic chip, physics and applications. So please join me to welcome him. Thank you.
So thank you for the nice introduction, and also thank you for the invitation from College of Optical Science in UA for the nice invitation. My name is Yang Li. I'm currently a postdoc fellow in Professor Eric Mazur's research group in Harvard University. And today I will introduce our recent work on the zero index on photonic chip physics and applications. So here, if we fill a glass cup with a regular medium with positive index, based on Snell's law, we know that the incident light and the refracted light were on the different side of the normal. In contrast, if we fill the same glass cup with a medium have negative index, similarly, based on Snell's law, we will see that the incident light and the refracted light were on the same side of the normal. But what will happen if we fill the same glass cup with a medium have a refractive index of 0? So in this talk, I will introduce the fundamental physics and the practical applications of zero-index medium. And then is our design of on-chip zero-index metamaterial. And eventually, I will show a proof of concept experimental demonstration of on-chip zero-index metamaterial. So first of all, what is zero-index? Any propagation of electromagnetic wave is governed by the wave equation. Here's in the form of Helmholtz equation. If we solve it, we found that the solution here is the traveling wave we assume propagate in the positive x direction. To guarantee that the phase is a constant, so the wavefront, as shown in the animation, will move towards the positive x direction. And based on the definition of the wavelength, which is inversely proportional to the refractive index in the denominator n, the wavelength inside the medium, whose refractive index is equal to 3, larger than the free space, is longer than the shorter than free space. And now, let's decrease the refractive index. We will see that the corresponding wavelength will become longer and longer until the refractive index reaches a magic number of 0. Now, the refractive index diverges, become infinity. What happened to the wave equation? Now let's look back. Because here refractive index becomes 0, so either or both the electric permittivity epsilon and magnetic permeability mu become 0. So the second term vanishes, only the first term survives. The Helmholtz equation degenerates to a Laplace equation, which means that the electric and magnetic phenomena decoupled. And what happened to the solution? Now let's look into the phase of this solution. Because the refractive index n becomes 0, and then the wave number k becomes 0, so the spatial phase term kx vanishes. Only the temporary phase term exists. And then here we can see that the corresponding electric field will keep as a constant inside the zero-index medium, but only oscillate as a function of time. So zero-index brings many extreme physics. when refractive index becomes 0, the wave number k becomes 0. And when the wave number k becomes 0, the corresponding wavelengths become infinity, as I mentioned before. So similarly, we can see that the phase velocity Vp also become infinity. How can a medium support a phase velocity of infinity? Now let's look down into the zero-index medium. So if we look into the phase of the input interface, we can see that it can reach that at the output phase instantaneously. So effectively, the phase velocity is infinity inside the zero-index medium. And finally, the spatial phase term, when the wave number k becomes 0, phi becomes 0, means there's no spatial phase allowance within the zero-index medium. Okay, so after introducing the fundamental physics of zero-index, let's have some fun. And from this question, we will figure out how does light couple into a zero-index medium. So the question is that if we send the light into a zero-index medium from free space with an incident angle 45 degrees, how much power can be transferred into the zero-index medium? Choice A, 50% of the incident power. B, 100%. C, 0%. D, none of above. So everybody can begin to think about the answer of the question now. And meanwhile, I will tell the rule about how to play this game. So when everybody is ready, I will count down from 3, and everybody will vote. The rule of vote is that everyone in the room will put their hand in front of the chest, and 1 finger means A, 2 means B, 3 is C, 4 is D. So let's begin to think. So in this round, please, there's no discussion, just the independent thinking. So anybody need longer time? Anyone? So if you know, let's get ready for the vote. So 3, 2, 1, vote. So now apparently D is dominant. D is not dominant. So I will not tell you the answer now. So in the next round, everyone please have a discussion with your neighbors, especially with those who made the different choice. So let's begin. What's your choice?
C, because the wavelength becomes infinite, so the energy of a respective photon is related to its wavelength. The shorter the wavelength, the more energy it has, and inversely it's true as well. So if the energy is shrinking to the point of reaching 0, then it must have 0.
I see. That's from the quantum point of view. I see. As what's your research area?
Mine's photonics and optical.
It's very cool. Yes, sir. May I know your answer?
Pardon me?
May I know your answer? What's your choice?
My choice was D.
May I know the reason? Why choose D?
Because 0, 50, and 100 are nice round numbers. It should be something else.
I see. It's very intuitive. Yeah.
No. So what's the answer?
You will know very soon.
Pardon me?
You will know very soon. You will know the answer very soon. I will tell you the answer in the talk right after this. Yeah. Have some patience to keep you here for a longer time.
Okay.
Yeah. Oh, sure. Thank you. So what's your choice?
I chose C, but I think it's wrong.
May I know the reason?
No real reason. No real reason.
Yeah, I can give you some hunches. Like you can think about from the Snell's law. Basically, it's like Snell's law and Fresnel's law. What is like a transmission corresponding to the Fresnel's law, and just substitute the refractive index into the Fresnel's law. Yeah. By the way, what's your major?
My major is optics. I'm just not a very good student.
You should be able to know. Yeah, for Fresnel's law. Yeah. So what's your choice?
I still don't know. I said none of the above.
So it's energy.
Still don't know.
I. Okay. So what's your choice?
C, 0.
May I know the reason?
Certain way.
Just by hunch?
I think if it went in, it would instantly be transferred very far away, and I don't like that idea.
I see.
That any power would appear. If that was a thin slab.
It's a half infinite space, yeah.
C, but I don't know why.
I give you some hint. You can think it from the Fresnel's law.
Yeah, he mentioned this one.
Yeah, that's the right direction to go. So what's your choice?
The hard part is the cosines. I only remember the
Yeah, that's right.
cosine.
Yeah. You're very close. Yeah. So what's your choice?
Thinking maybe it's
C. May I know the reason?
I think your index is small. You have a total internal refraction on the surface.
Very sharp. I know your answer.
Like C.
C. What's the reason? Why should
It's
C?
just like a total refraction.
I see. It's very sharp. May I know your choice?
I chose D.
What's the reason?
Because I expect something unexpected and seemingly weird to happen. But I'm not sure.
I see. So my know your choice. C. May I know the reason? Maybe. Okay, it's a good guess. So anybody need longer time for discussion? So if enough discussion, let's vote again. So 3, 2, 1, vote. Yeah, many people change their answers now. Now it's very diverse. There was some C, D is tight. Okay. So this is the time I will tell everyone the right answer. So the right answer is C, 0% of the incident power. And if you have no idea why C is the right choice, I will tell you the physics behind this answer in the next few slides. So now let's consider a general case. If we send a light into a zero-index medium from a lossless vacuum with non-refractive index, not a zero index, with an arbitrary incident angle theta I. And to consider how much power can be transferred into the zero-index medium, we have to consider the problem of critical angle theta C, which is defined by the right-hand side. And in the case N2 equal to 0, N1 does not equal to 0, the critical angle theta C become 0, means that any incident light with an incident angle greater than 0 will get total reflected, which means that there's no real power can be transferred into the medium 2 from medium 1. All the light will get reflected through the reflection angle direction. But to satisfy the boundary condition of electric and magnetic field in the tangential direction, there's still a wave in the medium 2. This wave is propagated along the interface and is fast attenuated in the direction perpendicular to the interface. So it is an evanescent surface wave. Only when the incident angle equal to 0, which means normal incident, part of the light can be transferred into the zero-index medium. Now to verify this answer, we have run a full wave simulation. This is a light incident into a zero-index medium from a free space with the incident angle 0, and we can see part of the light can be transferred into the zero-index medium. If we increase the incident angle from 0 degree to 45 degree, then the total reflection will happen. So here we can see that there's no real power can be transferred into medium 2 from medium 1 in the direction perpendicular to the interface. All the light is get reflected in the direction of reflection. And to satisfy the boundary condition of the tangential component of electric and magnetic field, there's still a wave propagated in the medium 2 in the direction parallel to the interface, but it's fast attenuated in the direction normal to the interface. So this is surface wave. And back to our question. In this case, the refractive index of medium 1 is equal to 1 and medium 2 is equal to 0. So the critical angle is equal to 0. And the incident angle, 45 degrees, is larger than the incident angle. So total reflection happened. 0% of the incident light can be transferred into the zero index medium. So C is the right answer. After introducing the fundamental physics of zero index, let's look into the practical applications of the zero index. The first application I introduce is interconnectors for integrated photonics. If we're looking into a PCB board, we found that electronics connect 2 points by electronic wires, which is very flexible and can be in arbitrary shape. On the other hand, similar to the integrated electronics, integrated photonics enable the miniaturization of various optical devices and systems on photonic chip. And in integrated photonics, they connect the 2 points through this curvilinear dielectric waveguides, which is inflexible and take huge footprint. Now, if we based on the zero index, we can achieve a supercoupling phenomena, which means that if we fill a channel with a zero index medium and connect 2 regular waveguides with positive index, we can achieve a high efficient tunneling between these 2 regular waveguides, regardless of the shape, bending, twisting, and the length of the zero index channel. So in some sense, this is an optic analog of electronic connectors. The second application is for wavefront engineering, including beam stealing and holograph. Now, we use the zero index medium to build a thin film above a silicon and open it to free space. And we guide the light into the zero index medium in the direction parallel to the interface. And because the momentum inside the zero index medium is equal to 0, and in the surrounding medium, either in the substrate and in the top, is greater than 0. So to satisfy the condition of momentum conservation, the light will couple into the surrounding medium in the form of plane wave. So here we can see in the animation, the light is coupled into the outer plane direction. Oh, go ahead.
Sorry, to go back to your last point, when you said that in order to satisfy the boundary conditions of the field, there's a surface wave or evanescent field, right?
Yes.
And so that's technically on both sides of the boundary, right?
Yes. Okay, so light is coupled into the outer plane direction in the form of plane wave. And by taking advantage of this outer plane radiation, we were able to achieve wavefront engineering application, here including beam stealing and holograph. And considering if the effective index of our zero index thin film is continuous change from positive to 0 and to negative, we were able to change the direction of the beam by changing the operating wavelength. Here, if the refractive index is equal to 0.01, then the beam points to a positive angle. Instead, when the refractive index is equal to negative 0.01, the beam points to a negative angle. The third application is in nonlinear optics. So in electronics, the transistors enable the control of large signal by using a small signal. Its counterpart in optics, we are able to control light by using another light based on the nonlinear optics effect. Here, a good example is a palm probe experiment. If we use a very strong palm beam to illuminate on a nonlinear material, and then we were able to change its nonlinear refractive index so as to change the optical behavior of the probing, such as the reflection and the transmission. But because of the nonlinear optical response is only a perturbation of the linear response, so usually most material only exists or only shows a weak optical nonlinearity even on the very strong and coherent illumination. To give a sense how large is nonlinear response compared with the linear response, here I give the linear response of most metamaterial is chi1 is in the order of unit. And the second harmonic term chi2 is in the order of 10 to the negative 12. And the third order chi3 is of the order of 10 to the negative 24. And if we're looking at a particular nonlinear response, here is the third harmonic generation. The signal is at the frequency omega. The pump is at the frequency omega, and the signal is at 3 omega. And the total refractive index of the medium is consist of two parts. The linear part, the first term n0, is a regular linear index of material. And the second part is a product of two components. The first one, N2, is an intensity-dependent index. And the second term, IN, is the intensity of the pump. So let's look into the intensity-dependent index, N2. Because, as we know, the chi3, the third order susceptibility, is usually ultra small in the terms of 10 to the negative 24. So the N2 here is a very small value. But if we pay more special attention to the denominator of the N2, we found that there's a linear index N0 square in the denominator. So when the linear index diverges, the intensity-dependent index N2 become an infinite number. When N0 becomes 0. That means that we can enhance the intensity-dependent index N2 by using a medium with a linear index equal to 0. This opens the door of controlling light by using a not very strong light. The last application I present here is in the quantum optics. The zero-phase advance in the zero-index medium allowed quantum emitters inside such a medium to emit photons coherently or in phase with each other. So if we employ this coherent property of zero-index to investigate several quantum optical phenomena, we were able to achieve some exotic behavior, such as superradiance. Superradiance here is a many-body phenomena in which emitters radiate coherently with one another. And then the effective constructive interference leads to the n-fold increase in the emitted light. Well, n is the number of the emitters. Here, we show a superradiant decay rates for various index of refraction in the system. This system here, including 1,000 emitters, are the function of the average inter-emitter distance. So as shown the result in the y-axis, you can see that we experience a massive enhancement in the decay rate when the refractive index of the medium becomes smaller. Eventually, when we reach the zero index, which is like a green line at the top, you can see that the enhancement ratio is 1,000 throughout the entire operating space, regardless of the distance. And we can utilize this superradiant phenomena to achieve a superradiant laser with ultra narrow line width. So by operating in the bad cavity region means that the line width of the cavity is much wider than the emitter line width. The enhanced superradiant decay rate, go ahead. This can be various of emitters. Usually it's like atoms traditionally. And in our experiment, we use like a diamond to build the zero index medium. So we use like color centers, like a nitrogen vacancy center and silicon vacancy center. Yep. Okay, so by operating in the bad cavity region, in which the cavity line width is much broader than the emitter line width, the coherence of the laser is predominantly dominant by the emitter instead of the cavity. So here, the enhanced superradiant decay rate of the emitters will lead to a narrow linewidth of the emitted light. So eventually, we can achieve ultra narrow linewidth laser. Considering so many interesting fundamental physics and practical applications of the zero-index medium, how can we physically realize it? Here, based on the definition of refractive index equal to square root of electric permittivity epsilon and magnetic permeability mu, we were able to achieve a refractive index equal to 0, but only epsilon equal to 0, or mu near 0, or even a piece of mantle will show zero index around its plasma frequency, because the epsilon of a mantle will crossing 0 around its plasma frequency. But to efficiently couple the light into the zero-index medium, we have to consider the problem of impedance matching. Here, if we send the light into a zero-index medium in normal direction, then the reflection coefficient, here lowercase r, is the ratio of the amplitude of the reflected light to that of the incident light. And the transmission coefficient 1 minus r is the ratio of the amplitude of the transmitted light to the incident light. And the reflection coefficient is defined by the right-hand side, in which the capital Z, which is square root of mu of epsilon, is the impedance of the zero-index medium. Now, let's look into the impedance matching issue of all these different cases. First, for epsilon near 0, only the denominator of the impedance becomes 0, and the reflection coefficient becomes 1. Simply means that all the incident light will get reflected by the epsilon near 0 medium. And secondly, for mu near 0, the denominator of the impedance becomes 0, so impedance becomes 0. And the corresponding reflection coefficient equal to 1. Here expressed as a complex amplitude. What does it mean? So looking into this case, we found the magnitude of the reflection coefficient equal to 1. Means that all the light get reflected, but there's a pi phase in the reflection coefficient. So the reflected light will experience an additional pi phase shift. And finally, as a common sense, most mantle will behave as a mirror in the optical region. So all these skins, they have impedance, they have a zero index, but they have poor impedance matching. Can we get a material with both epsilon and mu approaching 0 at the same time? If so, the denominator and denominator of the impedance will approaching 0 simultaneously, so the impedance Z become a finite value. And the reflection coefficient less than 1 means that part of the incident light can coupled into the zero index, double zero index medium, and with the rest get reflected. So this scheme gives us good impedance matching. But how can we achieve so? Recently, several groups have proposed that by using a square array of 2D infinity tall dielectric cylinders, we were able to achieve a Dirac-cone-like dispersion at the central of the photonic band structure. And if we plot the effective permittivity epsilon and the effective permeability of such a structure, we found that both of them were crossing 0 simultaneously and linearly at our Dirac-cone frequency. And most importantly, the effective impedance Z here is maintained a relatively constant value, around like value 1.7 at the Dirac-cone frequency. So Dirac-cone makes the impedance match the zero index. To better visualize the different refractive index in this Dirac-cone metamaterial, now let's excite the Dirac-cone metamaterial with this excitation with the electric field polarized in the pillar axis direction. And we will see the behavior of electric field in the Z direction. Go ahead. Do you have a question? Oh, it's fine. Yeah, we will see the behavior of electric field in the Z direction in the XY plane, which is a cross-section of the 2D pillar array. Now let's first look into the zero-index frequency. So here we can see that the wave is propagated from the background medium from the left into the zero-index medium at the center and back to the background medium. Here, the black dots indicate the position of the 2D dielectric cylinders. Where does the zero index come from? So the trick here is to look into the region in between the pillars. Because of the effective constitutive parameters is a consequence of the interaction of all the electric and magnetic fields scattered by the pillars in the array. So if we look into the region, we found that the phase of the E field in this region is uniformly distributed, indicating zero phase at once, which corresponding to the zero index. Now let's look into the negative refracting index wavelengths. Similarly, let's look into the region in between the pillars. We found that the behavior of the electric field form a wave propagating in the direction opposite to the incident wave. This is a backward wave corresponding to a negative index. And finally, let's look into the frequency corresponding to the positive index. In the region in between the pillars, we found that the behavior of the field indicates a wave propagating in the direction of the incident wave. So this is a forward wave corresponding to a positive index. The question for us is, can we make an on-chip Dirac-cone metamaterial with impedance matched zero index? If so, we'll be able to fabricate it with standard planar process at large area in arbitrary shapes. And it can be efficiently coupled with standard silicon photonic devices and other optical components. So our design here is begin with 2D infinity tall silicon pillars. If we want to fabricate such a structure on a standard silicon uninsulator substrate, we will hit the limitation of the fabrication because the tall aspect ratio of this pillar array. So by nature, we want to cut these tall silicon pillars to become shorter. But on the theoretical side, such shorter silicon pillars cannot give us a reasonable Dirac-cone dispersion at the center of the brane zone, corresponding to an impedance matched zero index. So our trick is to build gold mirrors at the top and bottom of the silicon pillars. So under the TM polarization with electric field polarizing the pillar axis direction and considering the imaging theory, these pillar arrays become optically or electronically infinitely tall, so as to give us a reasonable Dirac-cone dispersion at the center of the brane zone with impedance match zero index. So this is a structure eventually designed for fabrication. Silicon pillars on silicon insulator substrate. Gold mirror is at the top and the bottom, and the background polymer matrix, here we use SU8, just to use to physically support the top gold mirror. And here's the SEM to show our sample in 4 different fabrication steps. Step 1 is the silicon pillars on SOI substrate. Step 2, we deposit the bottom gold mirror. Step 3, we spin coating SU8 in between the pillars. Step 4 is a final device with the top gold mirror. With such a design, we are able to achieve on-chip zero index metamaterial with impedance matched zero index, which can be fabricated using standard planar process over large area in arbitrary shape, and it can efficiently couple to the photonic integrated circuits and other optical components. To theoretically prove our design, we have used 3D full-wave numerical simulation to calculate its effective constitutive parameter. Here we can see that both effective permittivity and permeability are crossing zero simultaneously at our design wavelength, 1550 nanometer. And most importantly, the effective impedance still remain a relatively finite value. Here's around 1.7, similar to the 2D counterpart. And also we have calculated its 3D photonic band structure. Here we can see that the Dirac-cone do show up around the center of the brane zone, gamma point, and our design wavelength 1550 nanometer. If we zoom in this region, we found that the cones consist of 2 linear bands crossing each other at the gamma point and our design wavelength 1550 nanometer. To better visualize this cone, we have calculated its 3D dispersion surface. We can see that the cone is consisted of 2 linear bands, which are blue here, touching each other at the center of the brane zone and our design wavelength 1550 nanometer. And the isotropic behavior of this cone shows that our Dirac-cone metamaterial have isotropic zero index. So in this section, we have designed an on-chip Dirac-cone metamaterial with impedance matched zero index at 1550 nanometer. So to proof of concept to demonstrate our metamaterial do have zero index metamaterial, we have demonstrated this experimental demonstration process. So our experiment demonstration begins with a silicon uninsulator substrate. So this is a top-down view of the chip. And the way we use to demonstrate the zoom index is very simple. It's an 8 by 8 unit cell consists of a right triangular prism. And the input of the prism is a silicon taper waveguide. Light is guided into the metamaterial prism through the silicon taper waveguide, and then is refracted out from the output facet. So what is output? If we zoom out, we found that the output is an actuated semicircle waveguide, and the light is come out from the metamaterial prism and is guided in the semicircle actuated slab waveguide, eventually scattered by its gold edge and captured by our infrared camera above the test chip. So here's SEM to show the test configuration. And in the zoom-in range, you can see the configuration of the metamaterial prism clearly. This SEM shows the overview of our test configuration. So light is guided into the metamaterial prism through a silicon taper waveguide, and then is refracted out from the metamaterial prism and scattered by the annual ring edge of the actuated waveguide. So before we jump into the measurement result, let's look into the interface between the metamaterial prism and the output actuated waveguide. So the behavior of the light in this interface can be simply modeled by the Snell's law. The incident angle here, 45 degrees, is a constant. The refraction angle alpha is a variable. And N slab is a mode index of the actuated waveguide, and N prism is a metamaterial index we want. After a simple manipulation, we can see that the metamaterial prism index can be expressed by the right-hand side. The only variable in the right-hand side is the refraction angle alpha. Means that we can obtain the metamaterial index by measuring the refracted angle alpha directly. A point of note, here the zero index corresponding to the refraction angle equal to 0 means that the refraction rate is normal to the interface. So now let's zoom out and look into the experiment result. This is infrared imaging taken at 1570 nanometer at our test configuration. The white dashed line indicates the position of the input silicon taper waveguide and the output actuated semicircle waveguide. The white angle indicates the refracted beam is right below the metamaterial prism, which is shining brightly at the top center of the imaging. So this is a direct observation of the zero index. To better visualize the change of the refracted beam as a function of the wavelength, here we have made this animation. So in this animation, you can see that the refraction beam shows positive index in the shorter wavelength region, cosine 0 around 1570 nanometer, and the negative index in the longer wavelength region. And to quantitatively analyze the refracted index of our metamaterial prism, we have made an annual ring cut along the edge of our actuated waveguide, and we flatten it, plot it as a function of the wavelength, and repeat such a procedure at every single wavelength of our measurement spectrum, so we can get so-called far-field pattern. And this result is in good agreement with the corresponding 3D FTDD simulation result. Both of them show that the refracted beam is near the center of the far-field pattern and shows positive index in the shorter wavelength region, a cosine 0 around 1570 nanometer, and negative refraction in longer wavelength region. And one last thing we do here is that at every wavelength corresponding to the refraction angle we have measured and the Snell's law I have mentioned before, we kind of extract the refracted index of a metamaterial prism. And here's the result. So we can see that both the simulation and experimental result shows that our metamaterial. Go ahead.
Sorry, what was I didn't understand. What was the yellow part representing on that graph?
Which side? The simulation or experiment?
I guess either.
The yellow part. Oh, the yellow part is corresponding to the refracted beam. Like if we look into, the yellow part is here. Probably you can note. Yeah, this is the yellow part, and only at a single wavelength. So, and now it's here. It's get flattened.
Oh.
And if we do the measurement at every single wavelength, like this, like beams, like shift from positive and 0 and negative.
So it's a constant cross section, physically that you're just showing for different.
Yeah, cross section of the beam.
Yeah.
Could you explain why we get the angle at like 1680 at 45? Like I understand you get that in the experiment, but it surprised me you get that in the simulation as well. Like
so you mean the beam here? Yeah, this is a very good question. So to explain this point, I would like to go back a bunch of slides. So this is a photonic band structure of our designed zero-index metamaterial. Shows the entire behavior of our photonic crystal. So our designer like zero-index wavelength is at 1550 nanometer. And the two bands, like these two linear bands, contribute to the zero-index is like two linear bands. But if you like, I cannot show like these two slides, 2D and 3D simultaneously. But it's like in the 2D, like if you still remember it, that's like only these two linear bands corresponding to the zero-index. So we only have a zero-index in our 2D structure. But in the 3D, we like make it finite, add the goal. So the structures will become way more complicated. So we not only have these like linear bands corresponding to zero-index, but also have these like side bands. We call it side bands, contribute to non-zero index. That is where the like this like side beam come from. So any further question about this point?
About those side bands, so can you get rid of them just by varying the size, or it's not?
So by using this like double mirror structure, only changes the size is we could not get rid of it. But currently, like we are thinking about use another method. It's called like bound state continue. If we like only use like a single mirror, or like by engineering like some very complicated structure, we can get rid of it. Like we can achieve like effectively 2D behavior in our 3D structure. Yeah. Okay. So, yeah, so both the simulation and the experimental result shows a negative index in the long wavelength region. And in this section, we directly measured the zero index of a Dirac-cone metamaterial at 1570 nanometer. And here's the conclusion. First, I have introduced the physics and applications of zero index. And then I have shown our on-chip Dirac-cone metamaterial with impedance matched zero index designed at 1590 nanometer. And eventually, I have shown our proof of concept experimental demonstration of directly measure of zero index at 1570 nanometer. Take-home message. For the first time, we unambiguously demonstrate an on-chip Dirac-cone metamaterial with impedance matched zero index in the optical region. This work has featured on the cover of Nature Photonics in the November issue of 2015 and has broadly promoted by several mass media. For example, the PBS, Boston Global, and HVE Spectrum. And I would like to acknowledge my team member, Dr. Shotakita from Professor Marco Loncha's group, working on the nanofabrication, and the field we working on the cylindrical design and also the measurement. Alright, he handled all the optical waveguide design. Doro, she was a junior graduate student in this project, so she's working on everything. And sorry, I still need to acknowledge the NSF for the funding support, and all the nanofabrication and characterization is done in Harvard CNS. And eventually, I would like to express my deep gratitude to our PIs, Professors Federico Capasso, Marco Loncha, and Eric Mozor. And also, thank you for your attention.
Any questions?